everyone! In today's video, we're talking about probability distributions and how they can be used in data analysis. This is part 3 in my Statistics for Data Analysts series, and you can find parts 1 and 2 here, and those went over descriptive statistics and inferential statistics. So let's get right into it. A probability distribution is a function showing the likelihood of all possible values a random variable could take. Now, what's a random variable? Great question. A random variable is a variable whose value is determined by the outcome of a random event or process. It can take on different values, each with an associated probability. A visual representation of a probability distribution is shown by plotting the possible values of a random variable along the x-axis and the probability of that variable taking on that value on the y-axis. Now, there are two categories of probability distributions: discrete and continuous. But to really understand these two categories, let's first quickly do a review of discrete and continuous data types. Discrete data is data that can be counted and has a finite number of values. For example, the number of oranges you can buy at a store. You can buy 1 orange or 2 oranges or 10 oranges, but you can't really buy 2.125 oranges. That is assuming we're not slicing oranges, which we're not doing that in the store. Continuous data, on the other hand, can take an infinite number of values within a specified range. An example of this would be the weight of the oranges that was bought. You can have 1 pound of oranges or 2 pounds of oranges, but you can also have 2.56 pounds of oranges or 5.1598 pounds of oranges. Similarly, a discrete probability distribution represents a random variable that can take a finite number of values, while a continuous probability distribution represents a random variable that can take an infinite number of values in a given range. In a discrete probability distribution, each value has a specific probability assigned to that value of the random variable. But in a continuous probability distribution, we can only assign probabilities that a value will fall within a certain range of values. The first type of probability distribution is a discrete probability distribution, and it is called a Bernoulli probability distribution. This distribution is used for events or random variables that only have 2 outcomes. Think flipping a coin. The outcomes are heads or tails. In a visual representation of this probability distribution, you'll see the 2 outcomes along the x-axis and the probability of the variable having each of those outcomes on the y-axis. It's worth noting here that the probabilities of the 2 events don't actually have to be equal like they are here. The probabilities of the 2 events just have to sum to 1. So let's say that instead of flipping a coin, this probability distribution was for whether or not it was going to rain on a given day. So the 2 outcomes would be raining and not raining. And let's say the probability for raining is 60% and the probability for not raining is 40%. So you can see here 0.6 and 0.4, they add up to 1, but they don't have to be equal. Now, this is a discrete probability distribution because the random variable can only take 2 possible values. The next type of probability distribution is a uniform distribution. This distribution is used when all the possible values of a random variable have an equal probability of occurring. A uniform distribution can be either discrete or continuous. An example of a discrete uniform distribution is for the random variable of rolling a 6-sided dice. The probability of getting any of the values 1, 2, 3, 4, 5, or 6 is equal, and there's only 6 possible outcomes, so it's a discrete probability distribution. On the other hand, a random number generator that produces floating point numbers uniformly between 0 and 1 is an example of a continuous uniform distribution. This is because there's an infinite number of values that this random variable can take on, and the probability of it taking on any of these values is the same. So this is a continuous uniform distribution. The third type of probability distribution is a binomial probability distribution. In this distribution, the random variable can take on one of 2 values, where one value is considered a success and the other value is considered a failure. In this distribution, you have n number of trials, and the x-axis contains the number of times a success was seen across the trials. Now, this may remind you a bit of the Bernoulli distribution, because in the Bernoulli distribution, our random variable also had only two distinct values, one of which was a success and a failure. And that is because a Bernoulli distribution is really just a special case of a binomial distribution. A Bernoulli distribution just has one trial, whereas a binomial distribution shows multiple Bernoulli trials within the same distribution. So if we go back to that example that was given in the Bernoulli distribution of whether it was raining or not raining, we can actually turn that Bernoulli distribution into a binomial distribution by taking more trials. So let's say we wanted to plot the probability of a specific number of days of rain in a week. Well, one day would be one Bernoulli trial. So along the x-axis, we would have the number of days that we saw rain, which we would say is our success. And on the y-axis, we would have the probability that we would see that many days of rain in the week. The fourth type of probability distribution is a normal probability distribution, also known as a Gaussian distribution. This is the distribution that you have probably seen quite a bit, and it's shaped like a bell curve. Most of the data is centered around the mean and tapers off to the left and the right of the mean. For this distribution, the x-axis is the values that the random variable can take, and the y-axis is the probability density for those values. Now, the normal distribution is a continuous probability distribution because there is an infinite number of values that the random variable can take. For continuous distributions, we use a probability density function because while we cannot assign probabilities to individual points in a continuous probability distribution, we calculate the probability over an interval by integrating the density function. An example of a normal probability distribution would be the weights of each item for a specific manufacturer. This is because when a company is manufacturing a product, they do try to make sure that the weight of the item is as close to the mean as it can be. The next probability distribution is a Poisson distribution. This distribution gives the probability of an event happening a certain number of times in a given time space. Here, the x-axis is the number of occurrences of an event, and the y-axis is the probability that that event will occur that many times in the given time space. An example of this type of distribution is the number of visitors at a website every minute. In this distribution, you generally have a parameter called lambda, which is also the mean number of occurrences of an event. Given this mean parameter, you can find the likelihood that an event occurred X number of times. And finally, the last probability distribution that I wanted to cover was an exponential probability distribution. This is used to model the time between events. The x-axis is the time or event duration, and the y-axis is the probability that the event occurs at that specific time. An example of an exponential probability distribution would be the time until a computer hardware part fails, given that there is a constant fail rate over time. It's also worth noting that an exponential probability distribution always takes a decaying shape. This is because the probability of the event happening decreases over time. Now, you may be wondering, why does it matter what probability distribution my data has? Well, there are a few things that knowing the probability distribution is helpful with. The first is that knowing the probability distribution of our data helps us in choosing the right statistical tests. Many statistical tests have underlying assumptions about the data that need to hold true when applying that statistical test to the data set. For example, if you want to run a t-test on your data set, the data set should be normally distributed. Therefore, being able to identify what type of probability distribution your data set follows is key to identifying the type of statistical tests that can be applied to the dataset. The second use of knowing the probability distribution of your dataset is feature transformation and better model performance. For many machine learning models, the data needs to be normally distributed. So you need to check whether or not your data is normally distributed. And if it's not, you would need to apply transformations on the data before you use specific machine learning models. The third use case of knowing probability distributions is probability estimations. If you you know the probability distributions of your data, you can estimate probabilities at different values or ranges of values of the data. The fourth use case is sampling and resampling your data. When you're taking a sample of your data, you want to make sure that the underlying data structure stays intact. And knowing your data distribution is definitely key in doing so. And finally, knowing the probability distribution of your data set will help in identifying outliers and anomalies in your data set. For example, if you see many data points that differ significantly from the distribution of your data, that can indicate that you have some anomalies and maybe even errors in your data set. All right, that is our review of probability distributions, what they are, what kinds there are, and why they are important to know. I hope this video was helpful to you. If it was, please make sure to give it a like and subscribe to this channel for more tutorials and data analyst, data science content. Thank you for watching this video, and I hope to see you in the next one.